Because we're in Blackrock Castle, we ask, what is the stars? And the famous Sean from Junior and the Paycock by Sean O'Casey. I often looked up at the sky and asked myself the question, what is the moon? What is the stars? Well, we like to think at Blackrock we have a fair idea of what is the moon and what is the stars, but actually that hasn't always been the case. And at the turn of the 20th century, the question of what is the nature of light, which is closely linked to the nature of the stars, was actually a burning question, no pun intended. And there was a very famous scientist called Lord Kelvin, and he was a major player in science, and at 1900 he gave a very famous presentation to the Royal Academy, the Royal Society in London. He was the president of the Royal Society, and he was basically asked to give a précis of the way things were about our understanding of the universe. And Kelvin stood up, and he was, he was that sort of rambunctious type of character. He had a sad end, incidentally. He actually committed suicide because he was some of the things that he suggested weren't believed by others, and there was a couple of people around the same time as him, or from the same vintage of him, also did that. So suicide has sadly always been with us. But he stood up and he suggested that we know pretty much everything that there is to be known about the universe. You have to remember that Isaac Newton had actually allowed us to explain why that happened and to predict how fast that's going to fall and so on. And lots of different things like motions of the planets were understood. We could predict where they would be quite accurately, in fact very accurately. We knew about how heat flowed and all sorts of different things. And this was the era of what we call Newtonian physics. And Kelvin stood up and said, basically there's only two things that we can't really explain. Oops, sorry. And there's two experiments which don't sound very interesting or sexy, but I'm hoping to prove something from them in just a second. One was called the Young's slit experiment, and the other was called the photoelectric effect. So sometimes what you do is, let's remember what we're trying to figure out here. What's the nature of light? So here's light, and I'm trying to think, what might it be? So I'm trying to come up with an experiment that helps me to understand the nature of light. There's probably 1,000 experiments were performed, all of which didn't really tell us very much at all. But the two experiments that stand out, that did tell us something, are these two experiments. Now, this is an interesting thing, by the way, about science and about skepticism. And just as a brief aside, lots of science is often treated as very linear in the way it develops. And we're told this brilliant person followed this brilliant person, and so forth. And it all builds sort of seamlessly, one thing on top of the other, with a sort of an inevitability. In fact, it doesn't. Science is all about, unfortunately, going down lots of dead ends before you actually chart your way towards something which is a better representation of how the universe in which we live at the moment operates. So these are the two experiments which did a lot of good. So the people who performed them became sort of famous in the physics world. So let's go to an experiment which is light is a wave. So I almost feel like Jennifer Aniston, but actually you could take that out of context and I have no idea what Jennifer Aniston feels like. Sorry. How she feels inside is actually what I did mean. I really did mean it that way, by the way. But you're a bad lot and you didn't help earlier. So suppose we do something very, very simple. Suppose we take a bath of water and we just put some waves in towards the water, and we have a hole in where the water goes. So you can't really see there's a hole here, but the water comes through. But because it's a wave, and I won't explain why, it's not that it's that difficult, but it sort of spreads out, and this is referred to as diffraction. So what you try to do is you say, well, okay, if I then put, let's just imagine in a mad moment that light is a wave. If I put it through a hole, one or two small caveats, but if I put it through a hole, then it's going to spread out if it's a wave. So what you hope to see is, if you put it through a hole, you get something like this, a wave. Now, I'll try to show you why that looks the same as this, and then I'm going to show you that we can actually do that right here in a second. So if you imagine then that these waves, you see where they're together, they kind of give you a brightness, and in between you can kind of see a darkness, yeah? So this kind of darkness, I'm not a graphic artist, so I didn't line them up as well as I possibly could have. But anyway, you can kind of see that there's a brightness here, then a darkness here, then a brightness, then a darkness. Yeah. So the waves are kind of higher, 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 and lower, lower. Okay. So it sounds like a quiz game. But you get that, and you can only get that if light acts as a wave. So here I have, and I can pass this around a second because I know you're all very skeptical, so you don't believe me. But here I have a piece of glass, and all that's on it is a series of black lines. Okay, that's all there's on it. And here I have a laser. It's a very powerful laser, so be very careful. Anybody who's falling asleep gets the laser. So if I pass the laser through a hole, so in my hand, okay, like this, then nothing very exciting happens because it's indistinguishable from that. But if actually I make the hole very small, which is the equivalent of putting kind of, slits. Slit, okay, isn't a circular hole, but it's an obstruction which is quite narrow. Then something really quite interesting happens if I put it through this. So this is not, some people know things like diffraction ratings and so on, and light that's being bent. This is just a plain piece of glass with black lines on it. There's no more happening in this than that. It's extremely simple. Yet when I pass this through it, I get, and if I turn the thing, I can move this, what we call diffraction pattern, around. Now, the only possible explanation for that you can come up with is that light is a wave. But and if anybody else wants to try it, because, what was his name, Randy, yeah, and so on, he probably would think that I was doing this, cheating. But if you want to try it, but don't put it to the side or twist it to the left, or don't. It's a very simple experiment that you do. It's easier to do with a laser, actually. So when you do with ordinary light, you have to be it's a little bit more tricky. But basically, you see this lovely pattern. I hope everybody can see that. Yeah. Okay. So what we've concluded from that, though, is there's a lot we conclude from. First of all, and that is we realise that there's a thing called the electromagnetic spectrum, and that red light has a certain wavelength. So that the waves, the distance between these peaks is a certain thing, if it's red. And if the distance between them is less, we perceive it as blue. And then you can go right on into the ultraviolet, into the X-rays, where your eyes don't actually see. We haven't evolved to see them. We can detect them with lots of types of detectors, but we don't bother as a species to worry too much about them, unless if you're an Irish part of the species, then the UV, you do worry about it, but most likely too late in the day. But then at least we have our homeopathy cures, so we're all, I'm just going to go out tomorrow and get burnt. But the thing is that we can tell that light acts as a wave. So this is great. So what we say, somebody says, hold on a minute, I'm a little skeptical. I don't believe what you're doing. So what I'm going to do is I'm going to do a different experiment to prove the point. And that's great, because that's what science requires. So, the second experiment, which is now we're proving that light is a wave, lots of them come along, but there's one that actually you try, which is this. It's actually, this is kind of the original diagram from the original paper. So what you do is you have a tube which is evacuated, and you have a thing called a photocathode. Basically it's a bit of metal. And you put a voltage between here and here. So, if you can get electrons to come off the metals are full of electrons, then they'll go from the negative side here to the positive. So you'll move electrons. Actually, that's actually wrong. It should be positive, negative, clearly. So, whoever said this is from the original papers, telling porkies, to be quite honest. So the electrons will move towards the positive plate. But the idea is fairly simple. It's just current flow, yeah? So you shine light onto this photocathode. Now, the prediction was quite simple. If I shine light on this, the electrons will absorb the energy from the light. The red light has a little bit less energy, and the blue light has a little bit more energy. You can measure the energy of it. We can measure it from even the other experiment. But the red light has less energy, the blue light has more energy. No big deal. You shine red light on this, and eventually the electrons will get enough energy and they'll fly off the surface. That's what you expect. I mean, you do the experiment, and quite frankly, you almost wouldn't bother to do it because you absolutely know that's what's going to happen. So there's really almost no point in doing that. It'll be a little bit like me saying, let's do the experiment. All right, great. That was really exciting. We knew that was going to happen. But in fact, that isn't what happens. You shine the red light and you wait for the electrons to go across, so you just measure the current, and nothing happens. So you think, right, I'll give it a couple of minutes, and you come back a couple of minutes later, still nothing is happening. There's no movement of electrons. You give it a nap, you go for lunch, you go on your holidays, whatever it is, you come back, there's still no movement of electrons. No matter how long you wait, the electrons never leave the surface. They never absorb enough energy from this light. But now you say, okay, I'm fed up looking at red light, I'm going to try blue light. So you turn on the blue light, and the electrons come off straight away. It's immediate. You turn to red, nothing happens. Turn to blue, they come off. Now, the reason why Kelvin was saying that we didn't really understand was because he was saying, hold on a minute now, if we just could understand how young slits, which suggests that light is a wave, and this, which suggests it probably isn't, how do we fit these two together? Well, he couldn't. But in fact, not only could he not fit them together, nobody could fit them together until along came a young fella called Albert Einstein, who realized that you have to look at what's happening in a completely different way. Instead of light being sort of these waves, it actually acts. Now this looks like a wavy. It's unfortunate that in a sense that they use a symbol that's kind of wave-like. But instead of being this sort of big wave, just kind of like, so if I shine a light, it's kind of a wave that's going out this way. The explanation is that the light is tiny. It's actually effectively, it acts like a particle. So Einstein said, well actually in some instances the light acts like a particle, and in some instances it acts like a wave. Now that's okay if you're a dress designer or something. Sometimes you design a black dress, sometimes you design a white dress. But if you're a photon of light, let's think about it. Here you are, you know, you're walking along and so on. So you come to this slit. I think now I'll be a wave. Well, I mean, why? Now do you want to be a wave? Why not now do you want to be a particle? No, it's a slit. I'm going to be a wave. This makes no sense. If you think about it, there is no reasonable, or there's no simple answer as to why a photon decides, we call these photons, the light decides, I'm going to behave in one situation under one set of circumstances, and in another set of circumstances I'm going to behave differently. Now why is this important? Well, we learn, yeah, I forgot to say that. So this is a real situation because in actual fact we have a problem here, and we still have a problem here. I taught this stuff for years, hundreds of years obviously, just years. And I remember I used to sort of try to, yeah, sometimes it behaves like a wave, sometimes it behaves like a particle, and then I started to think about this, and so I started to read it a bit more, and I started to ask some colleagues. I said, of course, because you don't appear stupid. You know when light goes through a slit and it kind of be, you know, you hold your hand up in front. But somehow it's as if you're not saying the word. Somebody else is. So, you know, when light sort of away, so that struck you as strange, and it turned out it's a bit like sort of therapy, you know. Yeah, I feel the same. So then you look in the books, and the books are actually very unsatisfactory until you start then to find people who've actually said the same thing in the literature. That it's a convenience that we simply then package this in a different way, which we call wave-particle duality. Now I remember at college being told, this is wave-particle duality. Obviously. And I remember thinking, yes, that's obvious, because the professor, the authority at the front of the room said wave-particle duality. It also sounded, you know, difficult, so it must have been right. So I wasn't skeptical enough at the time to actually say, well, you know, maybe because there's a danger here. Am I skeptical or am I thick? If you're skeptical, this is good. Who wants to be thick? Anybody have it? So, sometimes light behaves as a wave, sometimes light behaves as a particle. To figure that bit out, you have to get a Nobel Prize. So that immediately tells you that ain't trivial, okay? People say, well, you know, science can't explain that. Burn them at the stake. So if you're a bit curious and most of what makes science interesting is the things we can't explain. You get away with it. If you're poor El Giordano in 1584, you don't.